So today we're going to look on the chapter 4, which is the heat exchangers. Toward this section 4, chapter 4, we're going to have 3 assignments for you guys, which is by the end of each section, you're going to submit the assignment. Okay. So this section, this chapter, we're going to discuss about the fundamental concept of the heat exchanger, which is the extending of the the heat transfer process, combining of the conduction, convection, and the radiations, which you have the overall heat transfer efficiency, overall heat transfer coefficients UA. So you're going to look all the details of the element for the heat exchange processes toward the slide. So there are 5 subsections for this chapter. First, we're going to look on the type of the heat exchanger, and then in overall heat transfer coefficients, which is the derivation from the heat transfer processes, and then the principle for the log mean temperature difference method, or LMTD method, which is applicable for concentric tube. And then you're going to look as well for the correction factor, which is if you're going to apply the LMTD method, you need to use the correction factor. We're going to look on the chart that provided by the previous investigator. And then the second method for analyzing of the heat exchanger is the effectiveness NTU method, which is the second part. And then finally, very brief on the heat exchanger design and considerations. So for the first subsection, the heat exchangers. The heat exchangers, there are several types of the heat exchanger, where the heat exchanger is the process of the heat exchange between the two fluids at a different temperature. So one is hot and one is considered of the cold. And then different temperatures, and they are separated by a solid wall that occurs in many engineering applications. So the figure shows you shell and tube heat exchanger, which is containing of the tubing, okay, tubes, and then which as well contain of the connection pipe, which is fulfilling of the shell with the fluid. The device of the heat exchanger is used to make this exchange is called as the heat exchanger. So this is a tube, okay, and then encapsulate of this tube is shell, okay, so this is a shell. All right. So heat exchanger are typically classified according to the flow arrangement and the type of the constructions. Okay, so as you can see here, flow arrangement, whether it is according to the flow, counter flow, both in the one in these opposite directions, and as well with the parallel flow, and as well type of the construction, how the layout of the heat exchanger itself. The simplest heat exchanger is one in which hot and cold flow move in the same direction, which is known as the parallel flow. Or it can be in opposite direction, that occurs in concentric tube. Okay, so or double pipe constructions, which is given by this drawing. So as you can see here, one is containing of the outer tube and one with the inner tube. It can be the inner tube can run with the hot flow or cold flow, and the outer tube can run, either with the hot flow or cold flow. Okay, so in the flow arrangement, parallel flow arrangement, the hot flow and cold flow of the fluid will enter in the similar positions. Okay, in the similar, and the flow in same direction and leave at the same end. So when the flow enter with the hot fluid, the temperature, let's say that as here T, and then passing, and then the cold flow enter with another TC in, and this is T hot in. Okay, so the hot temperature, the hot flow will give the heat to the cold flow, where the hot flow will reduce the temperature and the cold flow will increase the temperature. Okay, and by the end of the flow, the hot flow will get the minimum temperature and the cold flow will get the maximum temperature. Okay, so that's for the parallel flow. And for the counter flow arrangement, the hot flow and cold flow enter in the opposite direction and leave at the opposite end. Okay, opposite direction and leave in the opposite end. So if you take the hot flow, enter in this directions, okay, or in this in this direction, hot flow, okay, and then it will give the heat to the cold flow, where the cold flow, that the same direction for this one is the exit flow for the cold flow, but the cold flow enter in this opposite directions. Okay, and then what will happen, the hot flow will give the heat, we release the heat to the cold flow, and cold flow will absorb the heat from the hot flow. By the end of the process, for the hot fluid, we get to the TH out, and the cold fluid will get the TC out, where TH in is in this direction, and this is a TC in. Okay. And another flow arrangement is called cross flow, where through the cross flow there are two types of the cross flow, where cross flow mix and cross flow unmixed. So this is a cross flow unmixed, and this is cross flow mixed. For the cross flow mix, it is not, the flow is not separated, which is the flow which is coming cross to the fluid, to the tube. They are going to be separated or being guided by the fin. Okay, so this is a fin, where the usage of fin is actually to increase the surface area, where for the mix counter flow cross flow heat exchanger, it is there is no fin viable in the sections. Okay, so alternatively, the flow may cross in the flow perpendicular to one another, where the fluid motion over them may be mixed or unmixed. The fluid is mixed because the fin exhibit motion in the direction that is transverse to the main flow directions. So there is a most common for the industrial application known as the shell and tube design. The most common, which is where the flow is enter to the heat exchanger in two sections. One is the shell and another one through the tubing. So it can be the hot flow can enter to the shell, or cold flow can enter to the shell, or it can be vice versa. Okay, and then the shell inlet and then shell outlet. Okay, so it also can be the front end for the tube inlet, and then rear end for the tube outlet. So this design contains a large number of tubes packed in a shell, and then heat exchanger takes place as a fluid flows inside the tube while the other fluid outside the tube through the shell. A buffer is added into the shell design to increase the surface area and to enhance the heat exchanging processes. So this is a common type for the shell and tube, where in the shell and tube, as you can see here, this is all the tubing, and this is the entrance, and this is another opposite direction. Okay. It also can be arranged that the layout for the inlet and outlet can be in the same position, where the tubing, there will a U-shaped tube, okay, where the inlet and outlet position in the same direction, and there is a U-tube sections. Okay, so which is the arrangement, the inlet either top or down, it is separated by this layout. Okay, it can be this one, let's say this is the inlet and this is going to be the outlet. Okay, and the flow will have a U-turn, U-shape, U-tube in the end of the sections, like this. Okay, so one is inlet and the other side is outlet. Okay, it is separated by shell. So shell and tube exchanger are further classified by how many shell and tube passes are involved. Like this, for example, it can be a single shell or one shell and two tube passes, or it can be a two shell and four tube passes. Okay. And another type of the heat exchanger, it can be plate and frame. So through this one, it is separated by a corrugated flow passages. So this is, you can see at the indoor unit that you can find in your domestic at home, which is to use for the air conditioning processes. So heat exchanger terminology, some of the heat exchanger known as a condenser, which means that the heat is rejected to the surrounding. Heat exchanger, in one of the fluid is cool and the other condensed flow through the heat exchanger. It's used usually for the heat rejection from the hot to the cold side. And then boiler heat exchanger, which is one is a fluid absorb the heat and vaporize the fluid. And then a space radiator, which is a heat exchanger that transfer heat from hot fluid to the surrounding space by the radiation process. And then as well, evaporator. So the evaporator, where the heat is taken from the refrigerated spaces, which is, you can find this in your refrigerator or in your freezer. Okay, so another important terminology for the heat exchanging is the overall heat transfer coefficients, or known as U. You can refer this one from our previous chapter, which is in the conduction chapter 2, for the reading, which is you have the UA value, overall heat transfer coefficients. As for the double pipe heat exchanger, which is, this is going to be involved a little bit with the internal flow, the derivation will be begin from the overall thermal resistance, where if you recap from the overall thermal resistance, which is occur for this material, this section, which is double pipe, which is running with the shell or outer tube. Okay, and this is a hot fluid running with the inner tube. Okay, so that is for the inner tube. So for the inner tube, which is running with the hot fluid, this is the cross section, where the hot fluid, the inner fluid temperature Ti, and then outer fluid temperature To. And then it will pass through a wall, which is, this wall is the cylinder. Okay, so this is the wall. And then the process that occurs in the hot fluid is the convections, and as well convection process also occur in the cold fluid sections. And then conduction process happen through the wall for the inner tube. Okay, so the wall for the inner tube, Di and Do, which is the difference of the radius. The inner wall surface and outer wall surface, AO and AI. So for the thermal resistance through the wall is given by this equations. So this is the thermal resistance for the wall tube, and this is for the conductions. This is for the convections. Okay. So, and this is for the hot fluid, and this is for this one for the hot fluid, and this is for the cold fluid. So double pipe, yeah. So for the total thermal resistance is given by this equation, R total. So total thermal resistance in the path of the heat flow from hot to cold fluid in the heat exchanger include the skin resistance associated with the flow, scale resistance from the wall falling, and as well the thermal resistance of the wall material. So the rate of the heat transfer therefore can be simplified as according to this equation, which is Q delta T divided by R, which is equal to UA delta T, or you can refer to UI AI, and UO AO. UI referring to the inner surface for the inner tube, and UO AO for the outer surface for the inner tube, whereby UI AI is equal to UO AO. But anyhow, UI is not equal to UO. Unless otherwise, AI is equal to AO. So what is term when AI is equal to AO? AI will be equal to AO when the radius for the inner is equal to radius for the outer. In this case, the thickness for the inner tube is considered as 0. So which means that UI equal to UO. So thus AI equal to AO. So which means in that condition, you just take U I over U. So in this condition, when the equation is called as overall heat transfer coefficients, so which is 1 over UO AO is equal to R total. So with this case, arc wall can be considered as natural log dO over di 2 pi kl, and then natural log Rho over Ri 2 pi kl. If you expand this equation, it will give you this one. Okay, and then expanding this equation will give you this T over K AM, where AM is logarithmic mean area, which is given by these equations. Okay, so UO is given by this equation, which we can simplify. Yeah, so this is, as I mentioned before, if you assume that T is approaching to 0, where Di is equal to DO, that you have UI equal to UO. So that means 1 over HI plus 1 over HO is equal to overall heat transfer coefficients. So when the tube are thin and what the side is to enhance the heat transfer, the total heat transfer surface area on the fin side can become as AS total equal to A fin plus A surface with the fin plus the surface without fin. So for short fin in the high thermal conductivity, we can use this total thermal area in the convection resistance relation, which is given by this equation. Okay, but this is not that covered in the syllabus because fin is not part of the syllabus content. Yeah, and if you have a falling is you imagine that throughout the year when you have a tubing that running with a fluid, then the fluid will have some resistance, and the surface of the tube is not that is not smooth. Then there is a resistance. When the time passing by, there will be debris, or there will be a deposit will attach to the surface of the tube, then this deposit will give a scale to the surface and will increase throughout the year. Then it will create a layer of deposit that will increase additional resistance to the heat transfer. So thus the total rate of the heat transfer will be decreased. So if you imagine that this is happened in the tube, there will be the extra thermal resistance, wall thermal resistance for your heat exchanger that will going to increase the overall thermal resistance. So which means that the overall thermal resistance is inversely perpendicular to the U. So if you can see the equation before, 1 over U A equal to R total. So which means that if the R total is increased, the U will be decreased. So the net effect is presented in the falling factor, which measure the thermal resistance introduced by the falling effect. So in this section, you're going to analyze a little bit on the falling factor introduced by the deposit, or the effect to the total thermal resistance. Okay, so in general, U is low for the fluid with the K values, for example, gas and gases. So this example, you can go through by yourself the calculation for the thermal overall heat transfer coefficient. Okay, so 1 over U, which is this is the thickness is approaching the 0. Okay, that 1 overall heat transfer coefficients. Okay, and then this is the calculation for the internal convections for the laminar flow. Okay, all right, and this is the effect of the falling. So you can go through the guided tutorial here. The effect of falling will be increased due to these two sections, which due to the internal flow, and this is outer flow. So the deposit that attached to the inner surface and outer surface. So as you can see here, from this calculation, the overall thermal resistance R, which is 0.0532, the convection resistance, the falling effect, the surface, this is wall surface, and this is due to the friction falling effect, and this is due to the convection effect. So 0.02654, this is almost 50% of the total thermal resistance happened by the internal flow. And then 0.008 plus 0.001, which is 0.09, which is almost about 16% of the overall thermal resistance due to the falling effect. So you will increase about 16% contribution by deposits. Okay. So from here, you can see that almost 90%. So it's not 16%. It's 19% of the total resistance decays due to the falling. Okay.